Alright, welcome back Weather Tech students. We're going to make another short video here to discuss a little bit about how we can look at weather maps, be it models, be it some current plots of upper air data, and start to determine what the relationships are between such things such as thickness and precipitation type, to be able to look at vorticity and start to think about how vorticity is affected and what the ramifications might be, and then spend a little bit of time also again practicing the idea of temperature advection. And so you'll see in this series of graphics that we're going to pull from a number of different sites. I encourage you to take some time, especially in this virtual environment, to gain familiarity with different websites that exist and just look at model data. You don't have to understand everything, but the more time you spend actually looking at some of these products, over time you will gain more comfort and familiarity, and that's going to do nothing but help you as you move forward at Valparaiso University and into your meteorological careers. And so here we're looking at a product from the GFS. This is looking pretty far out. You may see at the top smidge of your screen. It's valid for 0Z on Thursday, April 9th, 2020. The idea of this being close to reality at that time is probably pretty small, but it still gives us a chance to look here a little bit at advection. And so when we look at this map, the thing that probably sticks out like a sore thumb to you is a low there across western Kansas, a nice 992 low, ejecting out from some of our higher terrain there in the Rockies. And then you'll see on the map a number of red lines that are dashed, and those are going to be your 1,000 to 500 millibar thickness lines. So you can see here a 558 thickness, 564 thickness, 570, 576. So you can see these increments of 60 meters. And so you'll notice that a number of them are dashed in red, but then as we work our way higher up towards the poles, once we get down to this 540, they are now shaded blue. And so that's showing again the idea that even though it's not set in stone, when we start to see this 540 thickness, that values lower than that are oftentimes going to coincide with more of a wintry precipitation pattern. But what I want you to do in many ways is just kind of get a feel for how the thickness lines behave in conjunction with both our mid-latitude cyclone as well as our precipitation type, which is depicted on this map. And so what you will notice is as we have our mid-latitude cyclone, you can see some type of trailing feature here in the pressure lines, more than likely a warm frontal boundary extending out here. Again, we just talked a lot about Sanders and Doswell, and that we'd need a little bit more to be able to get a really good feel where the boundary is, but for this purpose we can probably estimate that there's a warm frontal boundary draped somewhere across this region. And so you can see that ahead of our mid-latitude cyclone, we're seeing a surge at a similar latitude as might be further west in terms of higher thicknesses. So here across central Illinois, thicknesses are around 5640. If we work our way west into the area with the trough, you can see that our thicknesses are substantially lower. Again, this idea with the trough coming in the wake of our surface feature here, we're going to have a lower thickness, colder air working its way into the region. Whereas out here in the plains and Midwest, this surge of warmer air ahead of our mid-latitude cyclone, it's going to have some influence from a ridge, warmer temperatures throughout the column, and therefore we're seeing our higher heights out ahead of our surface low. The other thing to note is, again, the model depiction here of precipitation. Generally speaking, areas here that have thicknesses greater than 5,400 meters, we're looking primarily at rainfall. However, once we get back into the colder air north and behind our cyclone, we start to see maybe a little bit of mixed precipitation. Again, this is all model created, and the idea that we're having a greater expanse of snow as our thicknesses drop to 534, 528, so on and so forth. And so there's a number of things that, again, we can really look to focus on as we work into thickness and start to think about how these are going to relate to other atmospheric features and what we can glean as forecasters from the thickness, the idea of actually calculating thicknesses. This will be the map that you'll see on your tasks within this week's handout. I encourage you to look at similar features in association with this surface low across here Missouri, and this would be from the NAM from recent days, and this would actually be before you actually have a chance to view this video. This would be from weekend here, Saturday, March 28th is when this valid time is located. So again, taking an idea and thinking of the principles of thickness and how they coincide with our mid-latitude cyclone. Now let's take a look a little bit at vorticity. And so here I'm looking at the NCEP model guidance. So you can see mag.ncep.noaa.gov. Here I've pulled some GFS data, and here we're looking at 500 millibar heights, 500 millibar winds, as well as vorticity, with brighter colors indicating higher values of vorticity. For these maps, anything below a value of 16 is simply being truncated as white, indicating that it's a lower value of vorticity. So let's go ahead and start this video. I'll try to stop at a certain point and we can kind of discuss what's going on with the vorticity. And so as we start our video, you can see that we see higher values of vorticity rounding the base of this deep mid-level trough. Again, higher vorticity with another trough. Not a whole lot out here in conjunction with a broader ridge. And so as we work our way into the day Saturday, let's go ahead and stop. We've taken our trough and we've kind of changed the tilt of the trough. One thing you'll start hearing terms of is positive tilted and negative tilted trough. And by this point, you can see that the trough is kind of just oriented north-south. Generally speaking, a neutral tilt. We can see some things going out ahead of this trough. See the spreading apart of our wind barbs going from even east of due south right ahead of the 500 millibar reflection of our low, and more of a southwesterly flow. So we get this feature again here known as diffluence. Think of driving down the interstate and you're in 3 lanes of traffic, and all of a sudden it spreads out into 5 levels of traffic. You're going to have things become a little less congested, and that's going to allow in many ways for some rising motion at the surface ahead of our trough. But here again we can look at the higher values of vorticity. Note that ahead of some of these we would be getting some cyclonic vorticity advection, and back behind this, maybe across western Kansas, looking at more of an anticyclonic vorticity advection. So if we step things forward a little bit more, here we're looking at 0Z on Sunday, so this would coincide with 7 p.m. Central Time on Saturday, and you can see a number of things going on this map. You can see this kind of ball of vorticity now, not really a lot of defined vorticity advection, but what you can see if you look closely again, a lot of diffluence, some very strong winds rotating around the base of this trough. And if we look at the day 3 outlook for severe weather, we're actually expecting a threat of thunderstorms from the Chicago-Valparaiso area southward, with some embedded pockets potentially even seeing a slight risk of severe weather. And that's not to say that every time we analyze vorticity we're going to expect to find severe weather coinciding with it, but it is another reason that we do look at features in the mid-levels of the atmosphere, because they can have ramifications on what we would expect in terms of precipitation, cloud cover, and even severe weather. And so we'll end this by looking again. Here we are Saturday afternoon. This is looking at the 850 millibar reflection. Here we're at the College of DuPage's website. They have a very nice suite of products that many students find intuitive and easier to read. The color scheme is oftentimes very nice on these. And so here again at 850 we usually are going to focus on 850 millibars for much of our temperature advection analysis. The idea that we're trying to minimize any influence from terrain, other surface features that can kind of muck things up a little bit. And here we're looking at just a little higher up, a little less of a frictional influence, a little less of that the heating processes going on near the surface, and removing that and able to get a truer feel for what the temperature advections might be. And so here the reflection of our low is right across northwestern Iowa, a very intense system expected to happen at least by this morning's NAM run. And so here rotating around that you can see some very strong winds out ahead of it across Iowa, much of Illinois, Wisconsin, up into Minnesota. Still some strong flow in the wake of this system as well, but it's probably not too hard for you to pick out where we might have some type of a boundary at 850 millibars. In fact, you can almost see where you'd have the boundary with a little bit of a pressure trough extending here maybe through Detroit and out towards Erie, Pennsylvania. And again, a warm sector here at 850 with very nice temperatures, cool air, this continental polar air mass spilling in behind our system. And so if we look out here, say we look for instance across Kentucky. Notice that the temperatures across Kentucky, although there's some ebb and flow, are generally speaking the same. And so even though we have strong flow, we're not necessarily advecting any significantly warmer or cooler temperatures. And so on this time, on this date, we wouldn't say there's a notable warm or colder advection across the state of Kentucky. However, if we work our way up into, say, Wisconsin, you can see that we have very warm temperatures here across areas, say, Chicago, Milwaukee, Janesville. Again, warm relative to what we have going on up across the Great North. And this southeasterly, southerly type flow is moving these warm temperatures northward into these cooler temperatures. And so we have a very nice, what we would refer to as warm air advection scenario going on across much of Wisconsin and up into Minnesota. However, if you're sitting in Omaha, Nebraska, or maybe Des Moines, Iowa, Kansas City, you can see that we're quickly transitioning what was recently warm temperatures into much colder temperatures. And if we actually slide back, again, looking here at Saturday morning, you can see Kansas City had temperatures that were quite warm. But even though we're going through the day, when one might expect temperatures to increase due to heat from our sun, we know how we get that incoming radiation converted to infrared energy that warms our atmosphere, we're actually seeing temperatures drop quite rapidly at 850 millibars. This is because of that cold air advection setup that's occurring in conjunction with our cold frontal boundary here at 850. Mind you, there's a number of other areas on this map that you can pick out warm and cold advections. We definitely still have some good cold air advection going on here across Oklahoma as well as Texas. You can pick out some strong cold air advection. Temperatures in the minus 20s if you look at my mouse over here across areas of Canada. And so if we take again a little, let's keep here at 54 hours. Help if I keep it at 54 hours and we go toggle over here. This is again looking at the same time. So again, if we look at 54 hours here, 54 hours here, you can really pick up this expanse of cold air advection across this area in conjunction with our cold frontal boundary. Good warm air advection. Again, you can notice Kentucky, there's a little bit here and there, but it's also going to be heavily influenced by what appears to be convection within the model, or rain and thunderstorms. Cold air advection as we highlight across Canada. And again, you can really pick up not too far away from this pressure trough where we see some type of warm frontal feature helping to increase our warm air advection across the region. And so that's a little bit of an overview of some map analysis. Again, I encourage you to do some of this, and we actually bring this up in your tasks for the week. And so your first task for the week is to look at some of these websites. We've talked about College of DuPage. I've brought up some pivotal weather, tropical tidbits. We're going to throw a number of them out there, and I encourage you, I really do, to take a look at what you enjoy the most. All of them have features that are quite useful, and so even here at the bottom I show you a map on twister data. There's a lot of different ways to visualize model output. And so take a look at what's going on at 500 millibar vorticity, temperature advection at 850, and I want you to start considering how these patterns relate to your upper level troughs and mid-latitude cyclones. Where do we find temperature advection? We've talked about it, but give it some time and get comfortable with some of these products and what we can derive from them so you're more comfortable as a forecaster. Number two, we have a map available on Blackboard where you can pull up 800 or 500 millibar vorticity, and I encourage you to just simply print one out as able and start to analyze where are we seeing cyclonic vorticity advection, anticyclonic vorticity advection, and start to think about where do we see those in conjunction with our troughs. Do we find more CVA ahead of or behind an upper level trough? Finally, number three, we'll put a larger version on Blackboard as well. The idea is this is the map I showed about 5-7 minutes ago. thinking about where our 1,000 to 500 millibar thicknesses are located at high values and how those might coincide with that surface load that's moving across the plains into the Midwest. Again, food for thought. I encourage you to give this more time and start to improve your meteorological knowledge on some of these relatively new parameters to you as you prepare yourself for the rest of freshman year and into sophomore and junior year. Have a great rest of your day and take care.